Thank you. Good morning, everyone. Welcome to my talk. Firstly, I would like to thank the organizer for giving me this opportunity to share math ideas with all of you. I'm sorry that I cannot join you physically. The organizer has kindly arranged this online report for me. I really appreciate the arrangement. Today, I will talk about the mathematical induction in the Finite Ramsey theorem for pairs. This is the structure of my talk. Firstly, I will review some background, which you might be very familiar with. And then I will talk about Ramsey's theorem for trees. And then I will focus on TT22 and state the main theorem and list out some references. Reverse mathematics was started in 1970s by Harvey Friedman and Steve Simpson. The main question of reverse mathematics is that what are the appropriate axioms for mathematics? Nowadays, we have the standard reference, the sense book, subsystems of second order arithmetic. So many of the background materials are actually from his book. In reverse mathematics, we talk about second order arithmetic. So we are going to use the language of second order arithmetic. In second order arithmetic, we have the first order part, which we use M. You can see the writing, right? So we use M for the universe of the first order part, and we use S for the universe of the second order part. Many of research has been done related to the existence of sets in the second order part. And today my topic actually is more focused on the first order part, although it is also related to the second order part. I will focus on the mathematical induction. So let me first give you some notations I will use. As I said just now, M will be the first order part of the model. And some of the models would be standard and some of the models are non-standard. You know, we have non-standard models of arithmetic. And so we use omega for the standard model of arithmetic. And M here could be standard or could be non-standard. But because in this talk, I will talk about the inductive strengths of some Finite Ramsey theorem. So because we have limited inductive strengths, I'm sorry that we need to focus on the non-standard models. Okay, but some of the results might also be applied to the standard model of arithmetic. Here, the second order part are supposed to be some subset of the power set of the first order part. In reverse mathematics, we have so-called the big five. We start from RCA 0, which assumes the existence of recursive set or computable set, and then move to the WKL 0, which assumes the compactiveness, actually, of the binary tree. And then we have a stronger axiom, ACA, and so on and so forth. ACA says every arithmetically definable set exists. Okay, exist means exist in the second order part. And in this talk, we will mainly focus on the first three parts of the big five. Of course, big five has more advanced, stronger versions, ATR0 and Pi11CA0, but not in my talk. And under this set existence axioms, we have the axioms for the first order part as well. So in RCA0, we assume that we have the usual axioms of parallel arithmetic PA. And also we have mathematical inductions. In the setting of Harvey and Simpson, RCA 0 only assumes sigma 1 induction. That is, we can do the mathematical induction for sigma 1 formulas. And together with the set existence axioms, we have so-called the big five. Now let me focus on the induction because I'm interested in the inductive strings of the set existence axioms. Actually, the mathematical induction is in a strong way. That is, if you have for all y smaller than x, phi y is true, then inductively you get phi x is true. You do the mathematical induction here for all x, then actually you prove for all x, phi x is true. When we say the sigma n induction, we mean that the inductive strength here stated in terms of phi is a sigma 0n formula. So this is the sigma n induction. Also in parallel, we have the sigma n bonding. Sigma n bonding, that means that if you have a finite part, that is n is the bond, n is the bond, and for every y under this bond, you have a witness, W, phi y, W is true, then you have a uniform bond, B, for the witness. Okay, so that is for all y smaller than x, there is a W, a witness, bounded by the by B, you have phi y W. This is so-called the B sigma n. When we focus our formula phi on the sigma n formulas. Okay, we restrict our attention to sigma n formulas, then we have B sigma n. Paris and Kirby has a classical result telling us that actually we have this hierarchy on the inductive strings. In the borderline, we have I sigma 1, 0. Of course, there are some researchers focusing on the so-called I sigma 0, even weaker than I sigma 1. But because we look at the big five, we look at from RCA naught. So RCA naught, because RCA naught at least assumes sigma 1 induction, so we start from I sigma 1. B sigma 2 implies I sigma 1, I sigma 2 implies B sigma 2, and so on and so forth. And this hierarchy is in a strict order. In other words, you cannot have I sigma 1 implies B sigma 2, and so on and so forth. So this is a real hierarchy. And how this hierarchy is related to our big five, well, if you look at the first three, when we reach to ACA naught, when we assume that all the arithmetically definable sets exist, then actually we have the full PA, piano arithmetic. In other words, we have the full induction. And before that, when we have RCA naught or WKL naught, we only have sigma 1 induction. So in these two systems, we have the sigma 1 induction. When we consider the mathematical induction in the statement of set existence, we want to ask the following main question. That is, what are the appropriate inductions for mathematics? Before I move on to the tree Ramsey, I want to say a few words about the P sigma 1. This is somehow a little bit weird statement. This statement says that, okay, if you have a partial function, not necessarily total, so some function might be, some part of the function might be defined, some of the part of the function may not be defined. And if you look at approximation of this f, this partial function, then that means you have a sequence like this, okay? So S0, S1, and so on and so forth until Sn. So maybe let me draw you a graph. Okay, so what it means is that f is the partial function from m to m, from the first order part of the universe to itself. So this is f, and last one is also f. Okay, and S0 might be an arbitrary number. And then because it is a partial function, so before S0, between 0 and S0, this part, okay, f can be total, can be partial, and we have a range of S0 under f. Okay, this range is bounded by S1. And if you further apply f, the part below S1 maps to some part bounded by S2 and so on and so forth. This is trivial if you look at the total function of recursive functions, right? You're repeatedly doing the recursive function. But if you just look at the recursively enumerable function, okay? So that means some part may not be defined, then the result may not be that trivial. Why? Because remember here, the universe may not be standard. And some part, although it is finite, can map to maybe a unbounded image, okay? And this P sigma 1 does not only say that you have bounded image in each step, but from this approximation, its length is n or n plus 1. From this approximation, it means if you iterately doing this this partial function f, then you still have a bounded image. Okay, so this is the P sigma 1. Originally, I want to find the inductive strengths from the viewpoint of I sigma n or B sigma n, and this indeed those are the mostly commonly used hierarchies of induction when we talk about the inductive strengths. However, the P sigma 1 is P sigma n is also useful sometimes, in particular when we talk about the Ramsey theorem. And what does P sigma 1 say? Well, P sigma 1 says for every sigma 1 formula, maybe I erase this part, it looks a little bit messy. So it says that if you give me a formula phi, and this phi defines a partial function, say like f, then for any length z, you can give an approximation. So this is the statement of P sigma, maybe P sigma phi. But if you focus on the sigma 1 formulas phi, then you will get P sigma 1. But unfortunately, this statement alone does not directly imply the sigma 1 induction. So we put the sigma 1 induction together with this statement to say, oh, this is my P sigma 1. What is the relationship of P sigma 1 with other inductive strengths? Now let's look at the result. The result says that sigma 2 induction would imply P sigma 1 and P sigma 1, which includes sigma 1 induction, of course, implies sigma 1 induction. And if you remember the result of Paris and Kirby, you also know that I sigma 0 I sigma 2 implies B sigma 2, which implies I sigma 1. Okay, so P sigma 1 and B sigma 2, it seems that they are in the same position in the hierarchy. but unfortunately they are not. They do not imply each other. Okay, so they are incomparable, and if you add them together, then they still cannot imply sigma 2 induction. So this is the strength of P sigma 1 in the classical hierarchy of mathematical induction. A classical result by Kreiser and Yokoyama says that P sigma 1 actually over RC naught is equivalent with, say, like the totality of the Ackermann function and equivalent with BME1. So BME1 is just saying that if you keep enumerate, say, like the sigma 1 formulas or some initial segments which false some sigma 1 statement in a tree, okay, in a finite binary tree, then if you have a finite collection of formulas, then in the end it will stop. That's the intuitive idea of using BME1. Now it's the time for the tree Ramsey. What does tree Ramsey say? Well, if we give a model of RC naught, well, M is maybe standard, may not be standard. We use 2 to the power of less than m, little m, to denote the collection of all finite binary strings of less than m. And 2 to the power of less than capital M means the collection of all finite binary strings in M. And here, the tree Ramsey theorem is it is in parallel with the classical Ramsey theorem. In classical Ramsey theorem, you know, we do the coloring on the n subsets of, or size n subsets of the natural numbers. We give the collection of size n subsets of natural numbers and give colors on that kind of subsets. And similarly for tree Ramsey, we use, say, like here, if you have X is a collection of binary strings, then we use X to N to denote the collection of all compatible subsets of N, subsets of X of size N. So for example, if you use 2 to the power of less than m, this 1 to 2, okay? So it denotes all the subsets of sigma and tau, where, for example, sigma is an extension of tau, or tau is an extension of sigma, not including the equal. So we need 2 points to do the coloring. And why not we include all the subsets? Why here the compatible in the first set may look a little bit weird in the very beginning. Why we need compatible subsets of X of size N? Why not we include all the subsets of X of size N? It's easy to understand. That is because if you include all the subsets of X of size N, for example, this is a set, then how can I, if you include all the possible pairs sigma and tau, then I can give an easy coloring, say like for all compatible sigma and tau, I give one color, and for all non-compatible sigma and tau, I give another color. Then you will never have a homogeneous full binary tree, because in full binary tree, you always have compatible subsets and non-compatible subsets. That's why in the tree Ramsey theorem, we focus on the compatible subsets of X, or usually we have the compatible subsets of 2 to the power of smaller than M. Okay, what does the tree Ramsey say? It says that if you give a coloring on the n subsets of 2 to the power of m, compatible subsets of 2 to the power of less than m to k, k is the number of coloring, then we have a homogeneous or monochromatic subset of H. So what do we mean by subtree H? Here, the subtree is in a very weak sense. This is the statement I quoted from the paper. And why it is in a weak sense, that means usually when we talk about the subtree, the sigma is in this set, right? Usually, and all its processors would also in this H. For example, if you have the string 001 is in H, then 00 it must be in H. But our subset or our homogeneous tree H, we do not require that it is closed downwards. We only require that it is a subset of 2 to the power of less than m. Just it is isomorphic to 2 to the power of less than m. Here I include both the finite version and the infinite version because later on the finite version would play an essential role for the result. So if H is isomorphic to 2 to the power of less than m for some little m in this universe, and the coloring restricted to the compatible subsets of H of set n is a constant function, then we say H is a homogeneous or monochromatic tree. And if we have H is isomorphic to the infinite binary tree, then we also say it is homogeneous. But usually the first one I would emphasize this is a finite tree. And TTNK says that for every such coloring with size n here and k many colors has an infinite homogeneous tree. This is the set existence axiom. And TTN is the union of TTNK. And the fact is that in the standard model, we have TTNK. This is a combinatorial statement. And what is the inductive strength of TTNK? Well, for TT1, more or less, we know some result about it. We have found that the TT1 implies B sigma 02, but not conversely. And TT1 does not imply sigma 2 induction. And if you look at the Ramsey theorem for singletons, then this one is equivalent with B sigma 2. And for TT22, we know that it implies B sigma 2. And by a recent result by the team of NUS, we found that the TT22 is not compatible with the WKL0. And in this talk, I will try to show you that the TT22 is not enough to show the sigma 2 induction, because we know that it is a statement implies B sigma 02, but how about I sigma 2? It seems like a new result, but actually we need the result from RT22, and the new techniques would prove a weak version of TT22 does not imply I sigma 02, but thanks to the result of RT22, which does not imply the sigma 2 induction, we can combine them together to get the TT22 does not imply the sigma 2 induction. And if you have n bigger or equal to 3 and k bigger or equal to 2, then the TT NK and RT NK, both of them are equivalent with ACA naught over RCA naught. Okay, to warm up, let's look at the proof of TT22 in ACA naught. How did we do that? So actually, the proof is quite intuitive, but I list out the proof in greater detail to show that the mathematical induction here is a little bit complicated. Why it is so? Because let's look at a most intuitive idea of TT22. So if you give me a recursive coloring or compatible computable coloring of pairs of strings in 2 to the power of less than m, then we consider a full binary T together with a coloring C0. Okay, so the C0 is a coloring from T to 2. And then the first step is that we first put the empty string in T. And what we do next is, so we build up the tree T from here, grow upwards. And this is the empty string. And from the C here, then we can get every string sigma has a coloring when it is paired with this one, okay, with the empty string. And how do we give another coloring of this empty string? Well, it's quite simple. If we can use the color 0, then we use it. So when we can use the color 0, so we can use color 0 if the color 0 is in some sense dense in the extensions of this empty string. But wait a moment, what do you mean by saying it is dense? Because all the colorings are on pairs. So because we fix this guy, okay, then we can treat it as colorings on the string sigma. So we can talk about, well, whether it is color 0 or colored 1, and if it is dense in the extension of this empty string, then we just use color 0. And intuitively, we will, our subtree, the binary subtree T would be in some sense extensions of empty string with the color 0. But if we cannot use color 0, in other words, 0 is not dense in this tree. Well, that means we have somewhere, say like this sigma, above it, all of them are color 1, okay? So then in this case, we will use color 1 instead. So the subtree T would from the extensions of sigma. This is our step 0. And in the inductive steps S+1, that is, let me just use step 1 instead. So in the very beginning, we have put the empty string in the tree T. And then, for example, the color of empty string is color 0. And next, we find 2 strings, sigma 0 and sigma 1. So that is the pairing coloring of sigma 0 and sigma 1 with the empty string is color 0 as requested by C0. And the next, what should we do? Well, we will consider the extensions of sigma 0 and consider the extensions of sigma 1. Because the color 0, according to the assumption of step 0, if C0 empty string is 0, then it is dense in this tree. So we do not worry about it. We worry about the color of sigma 0 and sigma 1. So here we will choose all the strings sigma so that its pairing with sigma 0 is 0, and its pairing with empty string is also 0. That means we will use the color 0 for sigma 0 when it is possible. But what if it is not possible? Then we will switch to color 1. And we do the same thing for sigma 1. And so on and so forth. So this is our step 1. If you follow this idea, then in the end, you will have a binary tree, of course. And what is the feature of the binary tree? So we have the color C0 based on the color C. And then the color C0 sigma would equal to the original color C sigma paired with every extension of sigma in this tree T. So in this idea, we can construct a binary tree T inductively. However, from the viewpoint of mathematical induction, this one is a mess. Why it is a mess? Because firstly, we need to know whether something is dense in the tree or in the subtree. And to make things worse, here, for example, in this sigma 0, when we consider the extensions of sigma 0, then what we need to consider is sigma is pairing with sigma 0 and together with empty string. When we consider the non-standard models, then this is a very bad situation. Why? Because in the second step, step 1, the second step, we actually need to consider coloring, so 0, 0, right? So intuitively speaking, this is not only one-dimensional, but two-dimensional, okay? Two-dimensional. And if you have, so when you move to a step S, which is non-standard, bigger than omega, then you will have a non-standard length of a non-standard dimension of the coloring. So it could be 0, 1, 0, 1, and so on and so forth. When you consider this coloring, then you can see that actually we have infinitely many possible colors from outside, at least bigger than omega, many possible colors. And this is the construction of T and C0, but you can see that once we have T and C0, from here we can construct a subtree T star maybe. This T is not a homogeneous tree so far. Sorry, I forgot to say that. But it has the feature that every extension of sigma is pairing with sigma has the same color. So actually we reduce this to a TT1, and this is even weaker than TT1. So TT1, 2, okay, we only have 2 coloring based on C0. We have 2 coloring, and the C0 gives 0 or 1 to a string sigma. Okay, so based on TT1, 2, we can find out a homogeneous tree. So from here, we know that the mathematical induction here is previous result says that over ACA not even, the solution of TT22 is not trivial. The previous result says that there is a computable two coloring of this 2 to the power of less than m is pairing with no sigma 2 homogeneous tree. And what is the solution? The solution is at least pi 0.2. This is under ACA not, or you can treat it as a result in the standard model. We need many inductions to prove the result. And what is the inductive strings? A classical result by Hurst says that RT22 would imply B sigma 2. Now TT22 can be treated as RT22 together with the tree structure. So the main question is that since RT22 implies B sigma 2, so it's direct for us to know that the TT22 can also prove B sigma 2. The main question is whether we can prove I sigma 2 from TT22. So let me give you the model. The model M is the model of RCA not with the induction B sigma 2 and not I sigma 2. And we first suppose C is a recursive coloring on the pairing. So in this strange model, can we have an infinite homogeneous tree? This is the question because the classical construction of the homogeneous tree for the standard model does not work here, or under ACA not does not work here. The second question is that what is the complexity of a homogeneous tree if it exists in this situation? And the third one is that if it exists, if you have an infinite homogeneous tree, then can we construct a homogeneous infinite tree preserving B sigma 2? And in this talk, I will answer them in a quick way. Suppose M is such kind of model, and K and M with, there is coloring with there is a recursive coloring C from the pairing. Sorry, this is a typo then. There is a recursive coloring C from the pairing to 2, such that we have no zero jump plus the sigma 2 cut I of M, a homogeneous tree. So this one says that actually we cannot have a solution. Sometimes we cannot even have a solution below zero jump and cut I. So in this sense, even if we have WKL 0, when we assume that all the infinite trees, infinite binary trees have infinite paths, we cannot have TT22, because if you have a no solution between below zero jump, then you have no low solutions. And so this is the result saying that in this special kind of coloring, we have no low solution. This is about the lowness. Then we want to find out the existence. Since the result of lowness is very disappointing, we cannot have a low solution. How about other solutions? Can we have, say, like an infinite tree? We do not require it is low. We do not require it is high. We do not give any bound on the complexity of the tree. Then can we have a solution? The answer is yes. And how can we find it? We use the Finite Ramsey. So if you have a model of B sigma 2, but not I sigma 2, The Finite Ramsey actually is a combinatorial theorem, says that if you want to have a homogeneous tree of high at h means it is isomorphic to 2 to the power of less than h. If you have, you want such kind of homogeneous tree, and A is the number of coloring. So this is the number of color. Then there is always a number S. This S is the Ramsey number. So if you focus on the coloring, on the pairing of high at S, then you focus on the this kind of coloring, then we always can find a homogeneous tree. The significance of this Finite Ramsey is that we do not require the number S depend on the coloring C. So to determine the number S, the high at S here, we only need to know, okay, the outcome of the homogeneous tree. How many levels do you want? Do you want level 2 homogeneous tree or level 4 homogeneous tree, and so on and so forth? And you only need to know the number of colors. So based on this, let me see just a few words about the construction. So how can you, intuitively, how can you construct a homogeneous tree? So we construct a homogeneous tree from here. So in the very beginning, we have a tree. Okay, this is part of the part of 2 to the less than m. So we get onto a S, which is a Ramsey number big enough. And in this S, first, inside this tree, we want to find a homogeneous tree. This is not a finite, this is not an infinite case as we want, but this is a starting point. Okay, so from here, as we have a homogeneous tree of finite 1, and then we can do a similar thing on the extensions of this tree. Because the Ramsey number does not depend on the coloring, so we can do the Ramsey construction on every subtree, okay? But I want to highlight one thing, that is when you consider the homogeneous tree here, for example, in this small subtree, not only you need to consider the pairing between the any two compatible strings here, sigma and tau, inside this tree, but also you need to consider its connection with its predecessors. Why? Because, for example, here the sigma and tau, sigma 1, tau 1, and sigma 2, tau 2, they all have the same color, C under C. But when you come to its predecessors, when we want to find an infinite tree, then you meet a trouble. They may have, say, like C, here we have a theta, maybe C sigma 1 theta, and C tau 1 theta. They never agree. Then, although they locally they are homogeneous, but those kind of homogeneous cannot be extended to the full binary tree. That is meaningless for us. So to solve this problem, when you consider the extensions of this extension, this black tree. So first you need to consider the coloring with its predecessors. So we have actually an array of the coloring with its predecessors. And we find a homogeneous tree for the pairing with all its predecessors, and then find a homogeneous tree among themselves. So that is, we need to take the predecessors and the local subtree both under consideration. If we do that, then actually we can make sure in this small subtree, locally they are homogeneous, and also is pairing with all the previous subtrees are the same, the coloring of such kind of pairing. And the problem is that different trees may have different opinions. Maybe all these trees with the, for example, with the empty string has color 0, and all the right-hand side with empty string, it has color 1. So we need to further shrink this tree according to the extensions of the strings in the first section. Okay, we need to do another shrinking so that the extensions, we need to cut off some extensions because some of them may not agree in the colorings. Then we have a shrinked section in the first part, and then move on to the second part, and so on and so forth. So we do back and forth applications of the finite Ramsey theorem, and in the end, we can construct a homogeneous tree, although it is not definable. So the natural question is that, can we have a definable homogeneous tree? This one we still do not know. This kind of idea only work from outside. We do not know whether we can find a definable solution. And here I insert another definition in the reverse mathematics when we talk about the inductive strings. That is, in the standard model, every bounded subset is finite. Okay, so if it is bounded, say like 100, then it is finite. But it is not true in the non-standard model. Some of them might be a cut. So that is, if you have even have a non-standard model of PA, the standard part is a cut, right? So it has it is bounded, but no, not finite. It is not coded in the set. So here from the construction on the last page, we can construct a regular homogeneous tree, but not definable. Yeah, I will speed up. I think I have only 1 or 2 minutes left. So the next question is that, can we find a solution, a homogeneous solution to preserve the B sigma 2? The answer is yes. And the construction is more complicated. And the general idea is that in the picture just now, we consider the extensions between them. We need to add one more layer or multiple layers to consider the forcing of sigma 1 formulas, whether we can force the existence of some witness by Cohen forcing. And from Cohen forcing, what we can find is some so-called GL1 trees. the GL1 trees, that is, we can force all the sigma 1 formulas. And from a classical result by Chongyang and Slayman, they find that if you have an infinite recursive binary tree, 0 prime, a recursive binary tree, and every path of T is GL1. So like our construction, we construct a tree so that it becomes GL1, forcing sigma 1 formulas. Then there is the infinite path T preserving B sigma 2. So this is the guideline to construct the tree so that it preserves B sigma 2. And why we need the P sigma 1 here? That is because when we force the sigma 1 formulas, here not only one layer, we need several layers of the construction. So in these layers, we need to enumerate the sigma 1 formulas that we can force. So because it is on the tree, we cannot guarantee that it can stop in any finite time without P sigma 1. So this is some part I do not like personally. I always want to find a solution so that without P sigma 1, can we still do it? So far, I still do not know the answer. Okay, so from here, we can get that we can have a tree, compute the C homogeneous tree so that it preserves the B sigma 2. Actually, this kind of construction can be generalized to the K coloring. That is, here I only talk about the construction for the TT22. That is, we only have 2 colors. But if you have K colors instead, can we still, K might be standard, might be non-standard. And it's more interesting if we consider the non-standard number. Because, for example, K is equal to 10, then you repeatedly use TT22 for 10 times, then you can get the answer. But for K bigger than omega, you cannot repeatedly use the TT22 for non-standardly many times. Then how to construct a solution. For the TT2, K is non-standard, we can still use the same idea to construct a homogeneous tree to preserve B sigma 2. However, this gives us one more problem. That is, for the TT22 and TT2, it seems like we used a similar construction with a little bit of modification. But can we say separate these two TT2 and TT22 and TT2? TT22, K here is maybe standard, maybe non-standard. So can we separate them from the viewpoint of inductive strength? I do not know. And another question I do not know is that whether we can prove the result for TT22 without this annoying P sigma 1, which is a strange inductive strength expression. So these are the questions I have not solved so far. And lastly, I want to focus another talk by Prof. Chong. He told me that he will give another talk in Germany, so I focused it. We're also looking at other tree Ramsey theorems, like so-called HL. So let me first quote this remark from Hurst and McNicon's paper, and they says that this weak form, that means the TTNK of isomorphism does not preserve the minima. That is, for example, I want the subtree here, right? So the sigma 1 may be equal to 0, 0, 1, and sigma 2 may be equal to 0, 0, 0. And then in this tree T, do we have the 0 as this string 0, 0 in this tree T? it may and may not be true for TTNK, because we only require the isomorphism. We do not require, okay, the minimum of these two preserves. We only require, say, like 0 or 0, 0 or empty string as in this tree T. We have another version of the tree Ramsey, which I cannot say it is another version. It is so-called the HL theorem, asked for a strong subtree. A strong subtree means that you take, say, like, this is the original binary tree. Let me draw it first. And when you take the subtree, you, for example, you take here and also take here. Okay, it preserves the minima. Why it preserves the minima? So it has two requirements. That is, the same level are from the same level. So that is, you cannot have one long and one short. This is one restriction. And the other restriction is that we must make sure that the two immediate successor, for example, here the empty string is in this tree T, and it has two immediate successors, and this two immediate successors has only two extensions in it. In other words, actually the minima is preserved in this sense. So this is the this kind of subtree is so-called the strong subtree. And HL theorem says that for the finite coloring of binary trees, we always have strong subtrees. And the complicated part of HL is that it does not only include the trees coloring, it includes the products of trees coloring. As trees product, it is not, say, like the TT22 coloring the pairs for this two, but the colorings of this two, that's the product. And we also have some results of the induction strings on the HL theorem. And so far we have found that the HL theorem at least need the sigma 2 bonding, but many versions does not need sigma 2 induction. This is the end of my talk. Here are the main references. Thank you for your time. Thanks.